Thanks for the opportunity. It's my first time coming back to Korea after COVID and first time in a quantum event. So if you have not met me, 만나서 반갑습니다. So let me start my talk. Today I'm going to talk about middleware, not the hardware, but the layer right above it. Q-Control is a scale up. We are about 160 people. We are headquartered in Sydney, Australia, but we have a very large presence in the US and a significant presence in Europe as well. And we do two things in the company. We build AI for quantum, solving what we think is the hardest problem in the industry, and I'll get to what that is. In two fields. On the left side, you see we work on quantum computing. Specifically, we build software that makes the hardware better. We improve quantum computing performance, and we are used by most prominent hardware companies. Easily more than 2/3 of companies that pass a certain size. And then on quantum sensing, we build software ruggedized quantum sensors for the US and its allies. And right now we are focused in the area of GPS denied navigation. In this particular talk, I will focus on the left side, which is in quantum computing. And infrastructure software is really the layer above the hardware. If you take the classical analogy, the IBM, Samsung, Dell, Intels of the world, infrastructure software above them is all your VMware, Red Hat, Citrix, Brocade, and all of those guys, and you can kind of see the valuations that they command. And then the layer above it is really application software. This is the piece that you take the fundamental hardware, your CPUs and now GPUs for granted, and you say, hey, I'm going to work on CAD software like Autodesk or graphical software like Adobe, so on and so forth. And then above that, you've got your platform as a service, cloud platform as a service vendors, AWS and Microsoft. The analogy in quantum is very, very similar. You've got AWS Bracket, you've got IBM Compute, IBM Quantum, you've got Microsoft Azure, and then there's a small set of application level providers. I've put some names there. But today, if you understand the direction of quantum compute, and if you followed how the industry has evolved over the last few years, the magic is really happening at the hardware level. Right? And the essential innovation that we brought to this field is the software layer that is just above hardware. Because of the problems that have been identified before, whether it's Grover search or any popular algorithm that you study in academics, you know that when you actually run execute on a quantum computer, there is a lot of noise, and that is what you see in the middle. What we introduced to this field is this construct called error suppression to drastically reduce the noise and be able to get the right answer typically within a few runs. And I'm going to talk about how we cut down overhead but through the use of our methods. So I'm going to posit that practical quantum advantage is limited by hardware error. It does not matter whether it's IBM, Rigetti, QEra, PsiQuantum, any of the names that I use in my presentation, every single hardware platform suffers from noise. And that's the single problem that we went after when we formed the company. And we have been around for nearly 8 years now. So the layers of software that we provide are just above the hardware, not the gray layer at the bottom, but the 3 purple layers above it, including the firmware compiler and the error correction. And the AI-powered methods, I know AI is very, very hot these days, but I'm going to de-emphasize it. I'm not going to talk much about artificial intelligence. It's used in our software, but I'm not going to talk about it too much. Instead, I'm going to focus on the type of results that we are able to deliver. And eventually the abstraction that we will be able to provide that makes application level stuff effective. So we have so we produce a suite of products that are fundamentally built around handling errors. And in fact, it's, the argument goes that we use many of these methods in our sensing as well, but we don't talk about sensing in this particular talk. For quantum computing, we have 3 products. One product is actually around building hardware. Let us say you're someone who is trying to build a quantum chip perhaps of a few qubits. You will need the equivalent of EDA, your old enterprise desktop automation, your Cadence and Synopsys, and all of the tools that you use to build semiconductors for verification such, even the BIOS, right? And I'm going to talk about a product called Boulder Opal, and there are many customers. We have, some of the customers that we work with are listed on the right side. I'm not going to read those out. The bread and butter of what we do is in error suppression, which is in the middle layer, our so-called Fire Opal product. And then finally, learning. When you are new to quantum compute, what you need to understand is not necessarily quantum physics, unless you're an expert. You need to understand just the minimum that is needed in order to use a quantum computer. Today, if you have, let us say, you have access to Yonsei's machine and you're able to access IBM or the QRM machine or whatever it is, you need to know enough to be able to set up a problem, focus on your algorithm, be able to run the algorithm on the quantum computer, be able to analyze the results, change the necessary parameters and rerun it, and eventually make your way towards scientific progress. What you don't want to do is figure out how the qubits work and noise characterization and spectroscopy, because that is an exercise that should be left to academics who are advancing the fundamental field, or perhaps researchers who work in national labs who may have special applications, etc. So I'm going to argue that the suite of products that we are building is towards enabling the general user of quantum computers, with the exception of the product at the bottom, which has been used extensively. We have over 50 customers who are using it for research purposes. The error suppression that we provide has given our customers results that were impossible to achieve before, and they have transformed the utility of the hardware, and I'm going to talk about it a little bit more. 3 specific examples, one by Capgemini around drug discovery, one around SoftBank. I was talking to a gentleman at SK Telecom earlier, but they used energy-efficient quantum kernels for network fault detection. I gave a talk on this in Tokyo. And finally, Deloitte, who used it for distribution loading. And when you use our software, you're able to run 10x deeper circuits. You'll be able to get to way higher computational accuracy and, in general, improved efficiency relative to what you might need on bare metal, or even if you use methods like error mitigation, which I'll just talk about. So over the past few years, we have set various world records. The world's largest quantum phase estimation demo, gate teleportation, the largest entangled state, constrained quantum optimization, the so-called QAOA algorithm, recently on the 156 qubits. Most of these were, I would say that all of these were run on IBM, and there is a publication behind every single thing. So it's peer reviewed and out there for you guys to look up. I also want to spend a minute telling you about the intersection between what we do in error suppression and error correction, and also this other thing called error mitigation. If you look at the NISQ era, noisy intermediate scale quantum era, error mitigation provides a certain amount of utility, but error mitigation involves taking the noisy output of a quantum computer, changing perhaps one parameter and doing the run over again, and changing one more parameter, running it, run and run and run and run for minutes, hours, sometimes days, and weeks, and eventually you get a result. A huge overhead. Today, our methods, error suppression, does the same thing without overhead, and the way we do it is by pre-characterizing the hardware. We deeply analyze the hardware for noise sources, and we are able to suppress the noise at the source, and I'll give you an analogy in a bit. In the future, error correction is coming. You heard from Oscar, you heard from Professor Kim, you heard from Jinsung. Error correction is coming. In its current formulation, it involves quite a bit of qubit overhead. If you want to do large-scale quantum computing, it's really the future is going to be a combination of error suppression and error correction, because error mitigation involves a lot of execution overhead. When you combine execution overhead with physical overhead, you run into some intractable problems that will just slow down the pace of progress in quantum computers. The other way to sort of visualize this is by comparing workloads. You can look at small financial simulations or state and phase estimation. These are small problems that involve typically about 10 precompiled circuits, a few thousands of shots. To run these types of problems on Q-control software typically takes, I don't know, a few seconds, whereas the same problem with error mitigation typically takes somewhere between 1 and 6 hours. As you get to larger problems, the medium-sized circuits, and this is really state-of-the-art today, which is, let us say I set up an icing spin glass problem, or I'm trying to do a quantum chemistry thing where I'm trying to understand the chemical ground states, or even quantum optimization problem, hundreds of circuits and thousands of shots. We are still talking about minutes with error suppression, whereas with error mitigation, for example, what you might find available in Qiskit, you're talking about days, right? In terms of the overhead that is introduced. And as you guys know, accessing quantum computers is not cheap. If you access it on the go, it is $1.60. That I don't know. Last time I checked, the pricing was $1.60 per second of compute time. Now, if you have your own dedicated machine that is available to you, sure, it's less of a problem, but still, eventually, it adds up. And then, in terms of larger problems, this is what the whole world is waiting for to unlock all those trillions of dollars of value, which is the so-called commercially relevant workloads. You want to run things like quantum optimization and quantum machine learning and such. Over 1,000 circuits, we can eventually get to the answer. If I'm doing vaccine discovery or any commercially viable problem that I'm investigating, I want to be able to get the answer within a few hours, even for the hardest problems that are tractable by, or that are suitable for quantum computers, not years. So traditional error mitigation, while I know is free, it's available, it has some fundamental issues. The other way to think about the combination of QEC and error suppression, what we do, which is pre-characterizing the hardware and running our pipeline, is this. So let us say you're in a room. It's almost July here. It's about to get hot. You run the AC. But what if your windows are open? And what if your door is open? You will have the leaky bucket problem, right? So your AC, sure, is working, but it's not efficient. You're wasting a lot of energy. Whereas what if I can shut the door and shut the windows? Now your AC is going to be much more efficient, right? So what we do is, if you are able to do very, very deep noise spectroscopy and a whole set of methods that we employ in our pipeline that I'm going to show, I think I'm going to show some of it in a bit. You will be able to not just cut the errors at the source, but at a runtime be able to take advantage of things like crosstalk mitigation and dynamic decoupling and all the methods that we have pioneered, and that typically allows you to push the hardware to its physical limit. And I'm saying push the hardware to the physical limit. We cannot push beyond the T1 limit, which is the coherence limit, but we are able to take advantage of the latent performance that is available in the hardware. You see, when you take a piece of hardware, it doesn't matter which vendor you choose from, there is hidden performance that is inside it. And that's the performance that we characterize and tease out with the way we work. One other example is one of our customers, Nord Quantique, published this earlier, and they were trying to set up a memory qubit with something called GKP, state preparation. And yeah, so with the unencoded bit, there was really, that's the reference that you see on the left side. Doing QEC and trying to implement a physical qubit is not pushing their logical timeline anymore. Right, and that's the logical lifetime that you see as TL in the y-axis anymore. But when they used our methods to suppress noise at the source, and they used our optimization methods, they were able to push the T1 lifecycle. So this is another argument for why error suppression makes sense when combined with QEC, and just keep your eyes peeled for more and more of this type of stuff. Jinsung spoke last. I'll also include a picture of Jensen Huang. Our belief is that the future is going to be all about hybrid computing. It's about hybrid data centers, and in order to do those effectively, you need to have very, very solid middleware. What I mean by solid middleware is middleware that's just not research code, middleware that has been proven out, that is actually providing great performance, that is compatible with everything else that is out there. And as I mentioned, we do 3 things in this company as far as quantum computing is concerned. One is build, and that's Boulder Opal. I've included some partners here for some very specific reasons. And then at the runtime, there's Fire Opal. And we have partnered with people like Classic, QBraid, Q-Centroid, Wolfram, which has the Mathematica product, as you guys know. And we have a whole set of system integrator partners as well as the learning piece. And the learning piece is very important. We have 29,000 users across the world when I checked last week, including the government of the UK, with the UKRI. One of the states in India adopted it last year and put 3,000 students through it. And now we have various scaling partners as well. And yeah, more recently, we enabled the Quantware chip. Quantware is a Dutch company, and their CEO gave us some very kind remarks. I'll tell you about what we did. We were able to take an uncalibrated quantum computer. It's a chip, maybe with the fridge around it and the basic control electronics. We helped with hardware characterization, component calibration, and essentially the gate tuning that I just mentioned that will push the hardware to the T1 limits, and performance validation that ended up with a whole number of parameters that were optimized. Now, the other way to think about it is at the extreme left, the basic chip that you have that you're building in your lab is suitable for no one because it doesn't do anything useful. It's a scientific curiosity, you're playing with it, etc. But after you put it through Boulder Opal and all of the work that we did, now you end up with something that is suitable for PhD level experts. Right? Now they can start to eke out perhaps some utility out of it, but what we call as the calibrated and characterized bare metal QPU. But now it's still not ready for prime time. You still are not able to run algorithms on it. That's when our Fire Opal product comes in. Things like circuit level error suppression, readout error mitigation, what we call as measurement error mitigation, and of course the compilation, which is always the first step. You end up with this nice abstracted high performance quantum processor. Anyone can go from a basic chip to a real high performing quantum processor with the help of the software tools that we provide, and that is suitable for any end user. Right? This is the reason why when people take hardware chips and build a quantum computer around it and put it up on the cloud for general consumption, they like working with Fire Opal because it improves the utility of the hardware. And so if you make the investment in what we do as a company in 2 or 3 years, you are starting to see first of all, the chip the computer that you'll have will be available to prosecute several use cases. You'll be able to run deeper circuits. You'll get results that are thousands of times better than the results that you might get on a bare metal basis. Larger problem size, number of shots that you need will reduce significantly, reducing your overall cost. And yeah, I mean, you'll be able to do way more projects than you were, rather than just battling the noise at the single qubit level. And yeah, hot off the press, we just put out the press announcement yesterday, and now our FireOpal product is now natively available with Rigetti, with their new 84-qubit Anka 3 device, and I believe in Korea, Rigetti is working closely with Norma, so we look forward to enabling them as well. And yeah, and already now that we have enabled Rigetti, customers are coming to us and saying, hey, we see that you enable Rigetti, how do we work with you to get better performance? And I throw out 2 examples here. One is Blue Qubit, the other is New South Wales. New South Wales government manages a lot of money, and they're interested in financial asset selection type problems, and Blue Qubit is more of a generalist, an algorithmic generalist. And then we also have been looking at what Network Rail is doing. By the way, this is the British railway system in England. And they looked at a very interesting scheduling problem, timetable, what's called as timetabling and platform allocation, because as you know, the London Tube is a very, very complex network, and being able to model out all the scenarios, so for example, adding more trains and more tracks and all of that is a huge problem, and quantum computing, because of the combinatorial optimization nature of the problem, is ideally suited for looking at this problem. One interesting investigation we did was, when you applied quantum computing to this problem, how much does it pull in quantum advantage by? So we looked at IBM's roadmap, and we looked at the gains that we provided with our error suppression software. It turned out that you get 6x better gains, and obviously thousands of times and reduced execution. We worked with IBM on this problem and saw that it accelerates the time to quantum advantage by 3 years. There's a case study that we have published on our website that we welcome you to take a look. And yeah, so other than Network Rail, things like convoy optimization, real-time transportation, and we also worked with Airbus and BMW on their challenge. And by the way, Airbus is also an investor in our company, in full disclosure. We think that, yes, chemistry is on track to be one of the first use cases, so will finance. But together with those, we think that transport optimization, scheduling, routing, and optimization may provide the first quantum advantage in 2 to 4 years. But that only happens when you combine the best hardware with the best software. If you don't have the best hardware, you might as well at least try to take advantage of the best software. Anyway, that was my last slide. I was very happy to come here and maybe tell you a couple of things about what we do, and happy to take any questions.